Hi, welcome to the optics lesson with Ryan and Ellen. Today, we will teach you the spectrum of electromagnetic waves, the dual nature of light, reflection, refraction, and mirrors. Please enjoy. So to begin the lesson, the spectrum of electromagnetic waves can be found by using a vacuum. If a vacuum was magically created by taking away all of the matter in a certain space, all of the electromagnetic waves would travel at the speed of light, which is 3 times 10 to the 8th meters per second squared. Now, whether in a vacuum or not, the speed, frequency, and wavelength are all related in the equation speed equals frequency times wavelength. There are lots of types of electromagnetic waves. These might include radio waves, microwaves, infrared waves, visible light, UV light, X-rays, and gamma rays. So as a type of electromagnetic wave, visible light is a part of the spectrum that the human eye can detect. The wavelength varies between 400 nanometers, which is red, and 700 nanometers, which is violet. The eye is most sensitive to a wavelength of 560 nanometers, which is yellow or green. Here's an interesting fact for you guys. Did you know that the center of the distribution of the sun coincides with the center of the sensitivity of our eyes? This is because humans have evolved so that their eyes are most sensitive to the wavelengths produced strongest by the sun. This enables us to see colors. Light is a tricky concept to grasp. Light acts as both a particle and a wave. In 1670, Newton provided a particle theory of light, which explained that light is a stream of particles with mass emitted by a source. Then 10 years later, Huygens showed that light is made of waves like sound. When light waves from a single source travels 2 different paths and arrives at the same point, they can combine or cancel each other out. This behavior is called interference. So as I said earlier, light can either travel in phase and combine into a larger wave, or travel out of phase and cancel each other out. Here's a quick reflection example. As you stare into the mirror checking yourself out, the face that stares you back is due to a concept called reflection. This also occurs as you stare into a lake and see the sky, also due to a reflection. When light traveling in one medium meets the boundary of a second medium and bounces off that surface, the light is reflected. When the surface is smooth, specular reflection occurs. When the surface is rough, this is when diffuse reflection occurs. Although it might seem that reflection is sort of random, there is actually a certain math behind it. The incident ray, or the ray of light from a source, hits the boundary of 2 mediums at an angle, which is theta, with the normal. The reflected ray bounces off the surface at the same angle. Here's a quick fact. Did you know that demonic red eyes are a frustration to many beginning photographers? The red eye effect in photographs is due to retroreflection. This happens when the light from the flash device enters the eye and reflects back along the original direction from the retina. The reflected light is red because of the blood vessels in the back of the eye. If the flash device and lens are close together, the retroreflected light enters the lens, giving you the red eye effect. Refraction is the change in direction of a wave due to a change in its speed. We all know that when a pencil is put in a glass of water, it looks bent, or that when white light passes through a prism, a rainbow is produced. When light traveling in one medium, let's say air, and passes through a second medium, let's say water, it bends, or is refracted. The index of refraction, n, indicates how easily light travels through a medium. It is harder for light to travel through objects of higher indexes. Think of a light as a particle. As it passes from air into water, it collides into and is scattered by more glass particles and takes a longer path to a certain point. Imagine that you want to walk through a hallway. When class is in session, there are no students in the hall, and it is easier to get from your classroom to the bathroom. During passing period, however, there is a crowd of students obstructing the most direct path, and it is harder to get from point A to point B, making you slower. When light travels from one medium to another, its frequency remains constant, but its wavelength and speed change. The wavelengths and indexes of refraction are related in the equation index of refraction 1 times lambda 1 equal index of refraction 2 times lambda 2. So how much does the light bend? This can be found by using Snell's law, which states that index of refraction 1 times theta 1 equals index of refraction 2 times. Waves of smaller wavelengths are bent more than waves of longer wavelengths. Now we will step into the realm of mirrors. Images produced by a mirror are either real or virtual. When rays of light actually meet at a point, a real image is formed. When the rays don't actually meet, but appears to originate from a point, the image is virtual. Real images can be projected on a screen, such as a screen at the movie theater. Virtual images cannot. The image produced by a flat mirror is always real. Side view mirrors, a reflective Christmas bulb, a curved mirrors in the hallways are all examples of spherical mirrors. They have a curved shape. Mirrors that curve inward are concave. You can determine if the image produced is real or virtual by ray tracing, but first you must understand how light is reflected by curved mirrors. Spherical mirrors have a radius of curvature r. The center of a curvature is a point C. A principal axis runs perpendicular to the mirror. Halfway between the center of curvature and the mirror is the focus, F. Here are some rules that you need to keep in mind. 1. When light passes through the center of curvature, it reflects along the same path. 2. When light travels parallel to the principal axis and hits the mirror, the reflected ray passes through the focus, and vice versa. For example, we have a concave mirror with a focus here and an object positioned here. The first ray travels perpendicular to the principal axis and therefore reflects through the focus. The second ray passes through the focus and reflects perpendicular to the axis. The point where the two rays intersect is the location of the real image. In another example, we have a convex mirror with a focus here and an object placed here. The first ray travels perpendicular to the principal axis and appears to reflect through the focus. The second ray reflects at where the principal axis meets the mirror. The point where the two rays appear to intersect is the location of the virtual image. Well, that's the end of it. Thanks for watching. We hope you enjoyed our lesson. Please stay tuned for a short example and our demo.